Hello everybody and welcome back. Root Beer here, and today we're going to finish off the 2014 Canadian Senior Mathematics Competition. So you can go back in this video series and see all the other questions, but we're going to tackle the final question, Part B, question number 3 in this video. Okay, so let's jump right in and take a look. It's the last question, very exciting. Let's take a look at question number 3. It even gets its own page. Alright, so for any real number x, this symbol, which we call the floor function of x, denotes the largest integer less than or equal to x. Okay, this idea comes up every once in a while. So for example, 4.2, the floor of that is 4, because 4 is the greatest integer less than or equal to that. Negative 2.4, well, you might think it's negative 2, but in fact, negative 3 is less than or equal to negative 2.4. So it's not about absolute value, it's not about magnitude, it's just about the ordering of the real numbers and the integers. Alright, that is, x is the integer that satisfies the inequality floor function x less than or floor function of x less than or equal to x less than floor function of x plus 1. Okay, there's going to be exactly one integer that satisfies that, and floor x is what we call that. So we got 3 parts to this question. First part, the equation x squared equals 3 floor x plus 1 has 2 solutions. One of them is x is root 7. The second solution is of the form x equals root a for some positive integer a. Determine the value of a. Okay. So it may appear like we have just one equation being satisfied, but because we have this floor function, we can probably work in this inequality somewhere, and that will probably narrow things down. Now, I don't like saying floor x, so I know it's an integer. I'm going to replace it with its own symbol, and since it's an integer, I'll probably call it n. All right, so we want x squared equals 3 floor x plus 1. Let n equal floor of x. Okay? So I might say that x is n plus y, and then y would have to be between 0 and 1, not including 1, but possibly including 0. That sort of notation might come up later. But n is definitely an actual integer. Okay? So we also know that x is root a. We are told that. Okay. So just to complete everything that we know, n is the floor of root a. Okay. Well, what can we do here? Okay, x squared is going to be a. It's 3 floor x plus 1, so that's just 3n plus 1. So a is 3n plus 1. Fantastic. Okay, so now we have a relationship between a and not x, but the floor of x. Okay. So n is the floor of root a, and we know from our inequality that n less than or equal to x less than n plus 1. Right? That's what makes n the floor of x. It's the unique n that satisfies this equation. Alright, not particularly helpful, but if we square this, we'll get a in the middle. N squared less than or equal to x squared, still less than n plus 1 squared. But we can expand that out and say n squared plus 2n plus 1. Well, that's a. And that's not particularly helpful either, but we have a whole bunch of n's here, and we have an expression for a in terms of n. So 3n plus 1 less than n squared plus 2n plus 1. So if we could solve for an integer value of n here, that could really help us. Well, if we rearrange it, if we subtract 3n plus 1 from everything, we'll be left with n squared minus 3n minus 1 less than or equal to 0 is less than n squared minus n. Yeah. So we need to satisfy this whole expression. Well, in order to do that, we could break it down into, we need to find n satisfying this inequality and n satisfying this inequality. So if we could solve both of those, that would be really helpful. Now this one's pretty easy to solve if we factor it. N minus 1. Okay. So this will be greater than 0 if both n and n minus 1 are positive. So n's positive and n minus 1 is positive. Or it's true if they're both negative. So 0 greater than n, n minus 1 less than 0. Okay, so we rearrange these. We can see that this is true if 1 less than n, or if n less than 0. Okay? So one of our inequalities is true if n is greater than 1 or n is less than 0. Okay? Then I guess this inequality will likely turn out to be, n will have to be less than or equal to, something like 10 or 7 or 13 or something like that. And then we'll have a bound on what n can be. Okay. Now, unfortunately, it doesn't look like there's a good way to factor this. So we'll have to use the quadratic formula. N squared minus 3n minus 1 equals 0. N is 3 plus or minus square root of 9 minus 4ac, so that's going to be plus 4 over 2. We're going to have 3 plus or minus 13 over 2. Okay, so there's that 13 I was mentioning. Yeah. Okay. Now, this positive a value here oh, geez, is it concave up or concave down? It's concave up is what it's called. So the one I mean is it's going to sort of look like this. So if we want to be less on the x-axis, we'll be between the roots. So 3 minus 13, root 13 over 2, less than or equal to n, less than or equal to 3 plus root 13 over 2. Okay. So we have both inequalities are satisfied if 1 is less than n is less than 3 plus root 13 over 2, or if, and this should be less than or equal to, or of 3 minus root 13 over 2 less than or equal to n less than 0. Okay? So what values could n be in this first range? Well, it can't be 1. It could be 2 probably. What's the square root of 13? So it's about 3.6. So we add 3 to it, we divide by 2. So n could be 2 or 3. And in this range, 3 minus 3.6 divided by 2, that's nothing. So only our first range works, and that's okay. So n is 2 or 3. Well, a was 3n plus 1. N equals 2 gives us a is 3 times 2 plus 1 is 7. Well, we already know that one. That's the one we were given. We were told square root of 7 is a possible value. So it's going to be n equals 3. 3 times 3 plus 1 equals 10. And I think we were just asked for the value of a. Yep, determine the value of a. And we could double check this by saying, okay, well, x squared, that's going to be 10. And then the floor function of square root of 10, well, square root of 10 is about 3.16, I think. So its floor would be 3. So 10 is equal to 3 times 3 plus 1. It all worked out. Okay, so that's A part. How about B? For each positive integer n, okay, so I might be seeking some new notation. Determine all possible integer values of the expression x squared minus 3 floor x, where x is a real number with floor x is equal to n. Okay, so we want all possible values of that expression. All right. Okay, I think I know where we're going with this. Okay, since n is equal to floor x, then we know that n is less than or equal to x is less than n plus 1. So if we square both sides, we get x squared less than n plus 1 squared. X squared and then less than n squared plus 2n plus 1. Okay. And now we want to add we want to subtract off of, so subtract 3 times floor x Okay. But we know what floor x is. It's just n. So n squared minus 3n square root of, and then we have x squared, floor 3, and then we have less than n squared plus 2n plus 1 minus 3n. So x squared minus 3n less than the desired amount. And we can simplify this. N squared minus n plus 1. And what exactly were we asked for? Were we asked for the values of x that give this range, or what was it? Determine all possible integer values of this expression. Okay. So n squared minus 3n, that's an integer just fine. Now we can't go up to n squared minus n plus 1. So we're going to get, but it's already an integer. So if we subtract off 1, we're less than that, and that's going to be the highest integer we can get. N squared minus n. Let's double check what we wrote. Yep, n squared minus n. So these are all the possible values that we can have. All of them are going to be integer values. And we can see there's going to be 2n of them. Or I guess 2 absolute value of n. But no, n's positive. Right? N is positive, right? N's a positive integer. Okay. All right. I'm pretty sure the positive integer part of that was probably very key. Yeah, because if n was a negative integer, we wouldn't have n squared and then n plus 1. Well, we would, but you wouldn't want to use that expression, I don't think. I don't know. I'm a tad confused. Oh well. This is our possible set of answers. Okay, that's what we're going with. So n squared minus 3n all the way up to n squared minus n. Okay, that's B. Now C part. For each integer k, with k greater than or equal to 0, determine all real numbers x, for which x squared is equal to 3 floor x plus k squared minus 1. Okay. So hopefully C part has some relation to A and B. And certainly the way that things have lined up on the paper, we can already see a little bit of a connection. If we rearrange this equation, we'll get k squared minus 1 on one side and x squared minus 3 floor x on the other. Well, we just did a question involving x squared minus 3 floor x. Okay. So we want all real numbers x that do that. Okay. Okay, so we can rearrange and get this formula. Let n be the floor of x. Now, unlike this previous question, which actually I was just going on about, n is not necessarily a positive integer. N can be any integer. Because we don't necessarily know that x is positive. Right? All real numbers x, says so right there. So n could be negative, and I think that's going to affect things. Okay. So what do we want to do? So the formula that I would use is a little different depending on whether n is positive or negative. So what do we want to do here? I'm actually going to say let n be the absolute value. That way the n I know I'm talking about is always going to be positive. That way when I subtract off an n, I know that I am subtracting off a positive amount, so my number is definitely getting smaller. Okay. So I can use the same sort of setup, and I'll get a range of numbers here. And then we'll have to look for 1 minus a square in there. That's the idea. That's the thinking here. Okay. Well, how about we start things off and we assume that we'll start looking at n positive. Okay. So suppose the floor of x is also is non-negative. I'm starting to rethink my absolute value symbols. No, I think it'll be fine. Okay, so we know that n is going to be less than or equal to x less than or equal to n plus 1. Okay, we know n squared less than or equal to x squared less than or equal to n plus 1. And we know n squared minus 3n less than or equal to x squared minus 3 floor x less than it was less than or equal to n squared minus n. Okay, k is an integer. So we're definitely looking for integer values of x squared minus 3 floor x. Okay? So, if we add 1 to this, we can just get a square. So k squared is going to have to be in this range. Now, depending on our values of n, we're going to get different ranges of numbers, and so we're going to get different squares. One thing I notice is that n squared minus 2n plus 1 is always going to be in here. So we're definitely always going to get at least one k value. But it's possible, we might get other squares just by accident. So we always have this possibility of k is n minus 1. Okay. But are we always only going to get that, or are we always? Can we get more? Can we always have k equals n minus 2? Right, those are the next two closest squares to n minus 1 squared. We know n minus 1 squared is always in that range. So we have to ask ourselves, when are other squares in this range? And if any other square is going to be in this range, it's either going to be n minus 2 squared or n squared. You know, we might have others, but at least one of those two will be in there. So I know that n minus 2 squared. Let's ask, when is he less than less than our lower bound. So we get n greater than, 3 less than n. So n greater than 3. So as soon as n is 4 or more, we're not going to have a square lower than n minus 1 squared. Okay, how about n squared itself? Well, n squared would be somewhere in the top of the range. So when is n squared bigger than this? Okay, well that would mean 1 is less than n. Actually, that doesn't make sense. We should have a 0 somewhere in here. Because what if n is 0? Then I have 0 minus 0 plus 1 is... Okay, so that's not true. Yeah. So combining both these facts, n greater than 3, or rather n greater than or equal to 4, only n minus 1 squared is in that range. So if n is greater than or equal to 4, we know k is going to just be equal to n minus 1. So eventually we will just have a general set of values of k where there's just always 1 or 2 or 3 possible values for x, but there's probably a couple special cases smaller. So n is 3. What is our range? Our range was n squared minus n squared minus 3n plus 1, n squared minus n plus 1. So if n is 3, 2, 1, 0. Let's leave a little space so we can have possible k values. N squared minus 3n plus 1, n squared minus n plus 1. So 3 squared minus 3 times 3, that's going to be 1. And then 9 minus 3, that's 6 plus 1, that's 7. So k could be 1 or k could be 2 in these ranges. We're looking for squares in this range. Right? We could have 1 squared or we could have 2 squared. We can't have 3 squared or 0 squared. How about in this range? Well, 4, for n equals 2, 4 minus 6, that's negative 2 plus 1, that's negative 1. So k is looking like it could be 0. 4 minus 2 plus 1, so that's 5 minus 2, so that's 3. So k could be 0 or k could be 1. Right? See, in these ranges, when n is less than or equal to 4, there are multiple possible squares in the range of values that x squared minus 3 floor x plus 1 can be. Okay, how about for 1? We get 1 minus 3 plus 1, so that's going to be negative 1. 1 minus 1 plus 1, that's going to be 1. So we can have 0 and 1 again. And for 0, we have 1 and 1, so k is definitely just going to be 1 here. Okay. So for n equals 4 is greater than or equal to 4, k is n minus 1. We know that's the only possible value, so n is equal to k plus 1, and then x squared minus 3n, which is k plus 1 is equal to k squared. We rearrange that, and we get x squared is equal to k squared plus 3k, that'll be minus 2, so it'll come over here and be plus 2. Now we're specifically only taking the positive values of x here. We should have a plus or minus here if we're just square rooting. But remember, we assumed that the floor of x was greater than or equal to 0. We assumed that. So we can't have negative values of x lying around, otherwise the floor of x will definitely be negative. Okay. So if n is equal to 3, we could have k equals 2. And that means that, so n, we know n is 3, k is 2. Actually, let's make another little chart. N, our possible k values are k squared minus 1 plus 3n, which is equal to x squared, and then the x. So n is 3, we can have 1 or 2. N is 2, we can have 0 or 1. So if k is 1, we get 1 minus 1 plus 9. X is equal, so this is going to be 9, x is equal to 3. For k is 2, k squared, that's 4, minus 1, that's 3, plus n is 3, so that's 12. So k could be, so x could be square root of 12. How about k is 0 here? Minus 1 plus 6. It's going to be 5, so we could have square root of 5. 1, that'll cancel out, and then we could have 6, so we could have square root of 6. Now let's continue on. We could have n is 1 and then 0 and 1, or n is 0 and just 0. K squared, no, geez, what was it? K squared minus 1, so that's going to be negative 1, plus 3 times n, that's going to be 2, so we could have a square root of 2 here. 3, so that's going to be 3, square root of 3 here. And n is 0, k is 1, so that's going to give us a 0, so we're going to get a 0 here. So now we have a whole bunch of possible x values in relation to not just the n's, but also the k's. And we're asked for x's in relation to k's, so we're probably going to have to make another giant chart at the end. And that concludes the assumption that the floor of x was greater than or equal to 0. Now how about if the floor of x is less than 0? Okay. Then we say floor of x is going to be negative n. Okay. And we know that negative n less than or equal to x less than negative n plus 1. Okay. Now if we square that, we get n squared and we get x squared and we get So I put the absolute values. I tried to make an absolute value to make this make sense. So we get n squared minus 2n plus 1. Okay, yeah, okay, that's definitely what we want to have happen. But is it? Yeah, okay. Yeah, that works. Okay. So n squared minus 3 negative n less than or equal to x squared less than n squared minus 2n plus 1 minus 3. And remember the floor of x is negative n. So we get n squared plus 3n less than or equal to x squared minus 3 floor x less than n squared plus n plus 1, I think. Okay, but we want integer values. So x squared minus 3 root x less than or equal to n squared plus n. And we drop the plus 1. All right. Now we want this to be equal to k squared minus 1. So once again, we're going to try and search for squares in a particular range. But this time we have to be mindful that n is going to be positive, but we're going to have negative values of x is what we're searching for here. Okay. So the great big question then becomes, what can we possibly have? We can have negative n plus 1 in this range. I'll be honest, this is a tad confusing as to what's going on, but I think I know what's going on. It's hard to keep track of it because I'm always going to have to put negative n, whereas normally I would want to put n minus 1, because I want to be talking about values of x that are negative. So I'm always going to have to be putting negative n's here. Alright, that's equal to n squared plus, oh no, sorry, it's going to be negative n minus 1. So k could be negative n plus 1. That's perfectly valid. K can be integers. No, k has to be positive, right? K has to be positive. Yeah, k is, well, not positive, but it's not negative. Okay. But n is definitely positive. So this shouldn't make any sense. Why do we have a 3n plus 1 and an n? These should be flipped around. I think I have to go back to the drawing board a little bit. Okay. Getting rid of this assumption because it's tripping me up. I thought it might make things a little easier. Alright, so if we change it to that, so it reads like that, n is still the floor of x, and we're just assuming that x is going to be positive. Actually, I should probably write that assumption in. Alright, so we're definitely going to have positive values of x. Now we're talking about negative values of x. Oh, went too far. Alright. So this whole page here is getting cleared. Okay, n is still the floor of x. So n less than or equal to n, less than or equal to n plus 1. But now we just have to remember n is going to be a negative number. Okay. So we still get n squared less than or equal to x squared less than n squared plus 2n plus 1. Okay. Oh, okay. I know what happened here. When you square it and x is negative, way back when, did I write x greater than 0 or x greater than or equal to 0? Okay, greater than or equal to. Okay, good. When you square negative values, the order is reverse. That's what it is. N squared plus 2n plus 1 less than x squared less than n squared. Okay, good. So I probably could have kept my other notation the way it was. I just completely forgot to switch the order around, because negative 2 halves is greater than negative 3, but when I square them, it becomes 2 halves squared less than 3. Okay. So there we go. So we could probably skip ahead, but let's write out a few more steps. So n squared, so we're adding on negative values of n. So minus n plus 1 less than x squared minus 3, floor of x less than or equal to n squared minus 3n. Okay. And we want integer values. So we just need to bump up this equal sign by 1, and it becomes a less than or equal sign, and it's going to be x squared minus 3 lor x less than or equal to n squared minus 3n. Okay, x squared minus 3 root n plus 1 is equal to k squared. So n squared minus n plus 3 less than or equal to k squared less than or equal to n squared minus 3n. All right. So we could have in this range right, we've got n minus n and a plus 3, so it's probably in this range. So we need to figure this out. We're going to have 2 less than or equal to negative n. So n less than or equal to negative 2, and then it'll be in that range. So n equals negative 1, we might not get this. Okay. But we probably will. Okay. So what other squares could we possibly have? Well, when is n squared out of here? N squared minus n plus 3. So that'll be n less than or equal to, or n less than 3. So we'll never have anything smaller than n squared minus 2n plus 1. So we'll never have k is equal to n, or I guess negative n or anything like that. How about n squared minus 3n plus 1 less than n squared minus 4n plus 4? Okay. Well, we get negative 3 less than negative n. So once again, n less than 3. Right? So that's negative n over there, negative 3 over here. The n squareds cancel out. And so we flip the sign by multiplying by a negative number. Okay. Okay, so those values will never ever be in the range. Okay. Oh, sorry, minus 2. So let's just double check, because once again I'm a little nervous with the negative signs. So that definitely switched around, and that was fantastic, and that made sense. So we came up here, we're looking for k squared in this particular range. So what does this range look like if we took in -4? So we'd get 16 plus 4 plus 3, okay, and then k squared, so 16 plus 12 plus 1, 29, okay, so those are all arranged properly. If n is -1, we get 1 plus, yeah. Okay. So it all looks like it's going to check out. So only when n is less than or equal to -2 will we have a candidate for k squared, and that'll be n minus 1 squared. Now, since k is non-negative, k will be 1 minus n. Okay, this makes sense because n is less than 0. So that makes sense, and we'll definitely get a positive value here. Okay, now what happens when we have this k value? Okay, so when we have this, we'll have x squared is equal to 3n plus k squared minus 1. Well, n is just going to be, so k minus, so it's 1 minus k. And this time we're going to take the negative root since we want to we assumed that x was less than or equal to 0, or less than 0. Okay. So we want to list everything in terms of k because that's the question, what the question asks us for. Now here, n is less than or equal to -2, so k will be greater than or equal to 3. So whenever we have k greater than or equal to 3, this expression will be a possible value for x. And when we have k is greater than or equal to 3, this will be a possible value for x. And then we have all the other possible values of x relative to k, so we just need to list them. Okay, so we're going to group them together. I'm going to do my best to remember them, but I will have to flip back and forth. Alright, so we could have k and x. We're going to have k could be 0, 1, 2, and then it could be greater than or equal to 3. So if it's 0, I may have to do this chart a little better, but I think we can manage. So we could have negative square root k squared minus 3k plus 2. And I think the other one, since we'll go back and check in a little bit, but I think it was 3k, or k squared plus 3k plus 2. 1, I know we had a bunch of values. I think it was 0, root 3, root 6, and 3. I think there was a root 12 for 2, and then I think it was root 2 and root 5 for 0. But I don't know. I might not have the best memory here, so we're going to have to check. So this one is fine. We need to check this one, and then I think it's root 12 for 2. Okay. K squared plus 3k plus 2. All right. When k is 2, we have a root 12, and that should be the only k value. With 1, we could have 3. With 0, we could have root 5. With 1, we could have root 6. And then with 1, we could have root 3. 1, we could have 0. And 0, we could have root 2. So I think we got them all in one go. Root 2, root 5, 0, root 3, root 6, 3, root 12, and our expressions. Oh, excellent, excellent. That's fantastic. Feeling good for my brain's short-term memory there. That's pretty nice. So, other than figuring out that fiddly, sorry, I misspoke there. Other than figuring out that fiddly little negative thing, I didn't think we really got caught in C at all. It was mostly straightforward. The method for B set us up really nicely. And now we have a little chart that for each integer k, we determined all real values x that satisfied this equation. Okay, so I'm not going to lie, that was somewhat of a long question, and I really do apologize for screwing up the negative sign stuff there in the middle. I thought I knew what was going on, and then I just completely forgot you switched the order of the squares around. So I do apologize that, and for that it probably added 5-7 minutes onto this thing that don't need to be there. But overall, I think it was a very straightforward question. C part, it might have been a little hard to get into, but definitely the way you approached B certainly helped. And A was, I don't think A was particularly hard, as long as you remember to use the inequality that defines the floor function. And that's something that you should remember when you try these contests. You might not think you can do all of 3B, or you might not think you can do number 10 or number 9 on the Euclid. But if they've got an A part, always try the A part, because oftentimes it's very simple, very straightforward. It's just sort of a calculation or an introduction to the concept. The harder stuff comes later. So an A part on B3 on the CSMC or the CIMC, or an A part on 9, 10, maybe even 8 on the Euclid paper, they're easier than the B's and C's. So much so that you could probably try it. And that gets you part marks on these contests, and that's something to keep in mind if you're actually writing them. And I do hope some of you out there are writing them, and I certainly hope that those of you who are planning on writing them are actually practicing these before you watch the videos. As usual, there's a link in the description for this particular contest, and you should be clicking on those and trying them ahead of time under the usual contest conditions. So time yourself, and don't use graphing calculators or anything like that. But all that said, that's the 2014 Canadian Senior paper. I think it was pretty good overall. And yeah, let me know what you thought of the contest, and if you liked the video, leave a like. I'll see you guys on another contest at another time. So long.